Imagine standing on a quiet hill at dawn, watching the sky burst into a symphony of orange, red, and pink as the sun rises. This beautiful sunrise is the final chapter in a long journey for the sunlight you see. Those photons began their odyssey in the sun's core, a searing nuclear engine that has burned for over 4.5 billion years. To understand how the sun formed, we must go back about 4.6 billion years before our solar system existed. At that time, in a calm region of the Milky Way galaxy, a vast giant molecular cloud of gas and dust drifted through space. This cloud was immense, spanning hundreds of light years and containing millions of times the sun's mass, and it was enriched with the remnants of ancient stars that had exploded as supernovae. Within this cosmic nursery were the building blocks of new stars, hydrogen and helium from the Big Bang, plus heavier elements like carbon, oxygen, nitrogen, and iron forged in earlier generations of stars. Such a rich mixture made the cloud fertile ground for star formation. However, a cloud of this size needs a trigger to collapse and form stars. Scientists think a shock wave from a nearby supernova explosion may have compressed parts of the cloud, causing it to fragment into denser clumps. One of these clumps would become the solar nebula, the dense region that eventually gave birth to our sun and solar system. As the cloud collapsed under gravity, it did not form a single massive object all at once. Instead, it broke into multiple clumps due to a phenomenon called the Jeans instability. Named after physicist James Jeans, the Jeans length is the critical size a cloud fragment must exceed for gravity to overcome internal gas pressure and trigger collapse. Different regions of the cloud reached this threshold at different times, leading to the formation of many protostellar cores rather than one huge star. One of these collapsing cores became the embryonic sun. This protostellar core grew denser and hotter as more gas and dust fell onto it, surrounded by a swirling envelope of infalling material. Over time, the core compressed itself into a tighter sphere under its own gravity. As it shrank, it began to heat up. Eventually, the core became dense and hot enough to evolve into a protostar, the early stage of a star. Even before nuclear fusion ignited, the protostar was emitting light and heat, powered by the energy released from gravitational contraction. However, its core temperature had not yet reached the millions of degrees needed to start nuclear fusion. The protostar continued accumulating mass for several million years, with its core temperature and pressure rising steadily. When the core temperature finally reached around 10 million degrees Celsius, something momentous happened. Hydrogen nuclei began fusing into helium, and our sun was born. The ignition of nuclear fusion in the core marked the birth of a star, as the sun could now generate its own energy and shine steadily. From protostar to main sequence star. At the moment nuclear fusion began, the young sun entered a new phase of its life. The energy pouring out from the core created an outward pressure that pushed back against the inward pull of gravity. This established a delicate balance known as hydrostatic equilibrium, where the outward pressure from nuclear reactions exactly counteracts the inward gravitational squeeze. With this balance in place, the sun stopped contracting and settled into a stable state on the main sequence of the Hertzsprung-Russell diagram, a long-lived phase in which a star steadily fuses hydrogen into helium in its core. This equilibrium is the defining feature of a star's life, a balance between the relentless inward crush of gravity and the outward pressure generated by nuclear fusion. This balance is a fundamental aspect of a star's life, as illustrated by the following diagram. As the sun formed, the leftover gas and dust swirling around it flattened into a rotating protoplanetary disk. The original cloud had some slight rotation, nothing in space is completely still, and as it collapsed, conservation of angular momentum caused it to spin faster, much like a figure skater speeding up when pulling in their arms. The rapidly spinning material flattened into a disk around the protostar's equator, while material along the spin axis fell onto the star. This spinning disk is where planets would later form. Within the disk, small particles collided and stuck together, gradually growing into planetesimals and eventually planets, moons, asteroids, and comets. Meanwhile, the young sun was surrounded by this pancake of material, some of which would be accreted into the sun itself or blown away by solar winds, and the rest would clump together to build the solar system we know today, with nuclear fusion sustaining it. the Sun settled into a stable adulthood on the main sequence about 4.5 billion years ago. It has remained in this stable phase ever since, converting hydrogen to helium in its core and radiating the released energy as sunlight. The Sun's main sequence lifetime is expected to last about 10 billion years in total, so it is roughly halfway through this stable period. As fusion proceeds, however, the composition of the core slowly changes. Hydrogen is gradually turned into helium ash. Over the past 4.5 billion years, this process has caused the Sun's energy output to increase by about 30%. The core becomes slightly hotter and denser as helium accumulates, which in turn raises the fusion rate and makes the Sun brighter. This trend will continue over the next several billion years. In about 5 billion years, the Sun will have exhausted most of the hydrogen fuel in its core. At that point, nuclear fusion in the core will diminish, and the balance of forces will shift. Gravity will begin to compress the core again, causing it to heat up. The Sun will then enter the next stages of its life, expanding into a red giant and later shedding its outer layers to form a planetary nebula, leaving behind a dense white dwarf remnant. But those events lie far in the future. For now, the Sun is a steady main sequence star, and we can study its inner workings to understand how it produces the light and heat that sustain life on Earth. The power of nuclear fusion in the Sun's core. Deep inside the Sun, in a region comprising only about the inner 25% of its radius, lies the core, the source of all the Sun's energy. The core is an astonishing environment. Temperatures there reach about 15 million degrees Celsius, and pressures are more than 250 billion times Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen atoms are completely stripped of their electrons, forming a plasma of bare protons and electrons. In this searing plasma, protons, the nuclei of hydrogen atoms, are moving at incredibly high speeds. Normally, two protons would repel each other due to their positive electric charges, the Coulomb force. Overcoming this electrostatic repulsion is the key challenge for nuclear fusion. Even at 15 million degrees Celsius, most proton collisions don't have enough energy to overcome the Coulomb barrier and fuse. In fact, early 20th century physicists were puzzled. According to classical physics, the Sun's core seemed too cold for fusion to occur at the observed rate. The solution to this puzzle came from quantum mechanics. In the 1920s, scientists realized that particles can exhibit wave-like behavior and have a probability of quantum tunneling through energy barriers even if they don't have enough classical energy to surmount them. In the Sun's core, quantum tunneling allows a small fraction of protons to effectively tunnel through the repulsive barrier and get close enough for the strong nuclear force to take over. The strong force is much more powerful than electromagnetism, but it only acts over extremely short distances, on the order of femtometers, or 10 to 15 meters, about the size of a proton. If two protons can tunnel to within that range, the strong force will bind them together, and fusion can proceed. The dominant nuclear fusion process in the Sun is the proton-proton chain reaction, which accounts for roughly 99% of the Sun's energy output. This multi-step process converts hydrogen nuclei, protons, into helium nuclei, releasing energy in the form of gamma-ray photons, neutrinos, and kinetic energy. The proton-proton chain can be broken down into three main steps. First step, two protons fuse together. One of the protons transforms into a neutron via the weak nuclear force, resulting in a nucleus of deuterium, a heavy isotope of hydrogen, consisting of one proton and one neutron, along with the emission of a positron, the antimatter counterpart of an electron, and a neutrino. This step is actually quite rare and slow. It requires a proton to undergo beta-plus decay at the moment of collision, which doesn't happen very often. But it's essential because it creates deuterium, which can then fuse further. The positron quickly annihilates with an electron, producing gamma-ray photons. Second step, the newly formed deuterium nucleus fuses with another proton. This produces a nucleus of helium-3, two protons and one neutron, and releases a high-energy gamma-ray photon. This step happens much faster than the first, so once deuterium is made, it readily combines with another proton. Third step, two helium-3 nuclei, each with 2 protons and 1 neutron, collide and fuse together. The result is one nucleus of helium, 2 protons and 2 neutrons, and 2 protons are released. This final step also releases energy in the form of gamma rays and kinetic energy of the particles. Essentially, 4 protons have been converted into 1 helium, nucleus, 2 positrons, which become gamma rays, 2 neutrinos, and several gamma ray photons. The net result of the proton-proton chain is that 4 hydrogen nuclei, protons, are fused into 1 helium, nucleus. The helium, nucleus has slightly less mass than the combined mass of the 4 protons. This missing mass is converted into energy according to Einstein's equation E equals mc². The energy is carried away as gamma rays and the kinetic energy of particles, which eventually escapes the sun as heat and light. Every second, the sun converts about 600 million tons of hydrogen into helium, and in the process about 4.3 million tons of mass are converted into energy. That is, the sun is losing 4.3 million tons of mass each second, an enormous amount, equivalent to the mass of about 3 million cars being turned into pure energy every second. This energy release is what powers the sun and provides the sunlight and heat that sustain life on Earth. By the way, the other 0.1% of the sun's energy comes from a secondary fusion pathway called the CNO cycle, which involves carbon, nitrogen, and oxygen as catalysts. The CNO cycle is more efficient in hotter stars, but in our sun it contributes only a tiny fraction of the energy output. The energy produced in the core in the form of gamma rays doesn't escape the sun immediately. Instead, those photons must make an arduous journey through the sun's interior, bouncing and scattering countless times, before they finally reach the surface and fly off into space. Let's follow one such photon on its long trip from the core to the sun's visible surface. Layers of the sun, from core to photosphere. The sun is not a uniform ball of gas, it has distinct layers with different properties. From the center outward, the main layers are the core, the radiative zone, the convective zone, and the photosphere, the visible surface. Each layer plays a role in how energy generated in the core is transported outward to eventually become sunlight. Understanding these layers helps us piece together the sun's structure and behavior. The core, the heart of the sun. As described, the core is where nuclear fusion occurs. It extends from the center out to about 25% of the sun's radius, around 170,000 kilometers. Despite being only a quarter of the radius, the core contains nearly half of the sun's total mass because it is incredibly dense, roughly 160 grams per cubic centimeter, which is over 10 times denser than lead and about 150 times denser than water. In fact, the core is so dense that if you had a teaspoon of core material, it would weigh about 1.6 tons. The temperature at the very center is about 15 million degrees Celsius, and the pressure is astronomical. In this environment, hydrogen is fused into helium as described, releasing energy. The energy is initially carried away in the form of high-energy gamma-ray photons and neutrinos. Neutrinos, being very weakly interacting, stream out of the core immediately, and out of the sun entirely in just a few seconds. In fact, neutrinos from the sun's core reach Earth in about 8 minutes, almost as fast as the light does, and pass right through the Earth largely unaffected. The photons, however, are another story. They begin a long diffusion process through the outer layers. In the core, photons can only travel a short distance before they collide with an electron or ion and are absorbed or scattered in a random direction. This means a photon doesn't take a straight path outward, instead it undergoes a random walk, constantly bouncing off particles. It's like trying to move through a dense crowd where you get jostled in random directions with each step. A gamma-ray photon might be absorbed by an ion, which then re-emits a photon, possibly at a lower energy, in a random direction. Through countless such interactions, the photon gradually migrates outward, step by step. Because of this slow, diffusive journey, it takes a very long time for energy to escape the core. Estimates vary, but a typical photon might take anywhere from 10,000 to 170,000 years to travel from the core to the surface of the sun, some models even suggest it could be longer, up to a few 100,000 years, depending on the exact conditions and how the random walk plays out. During this journey, the photon's energy also changes. High-energy gamma rays are repeatedly absorbed and re-emitted at lower energies, so by the time photons reach the outer layers, they are mostly visible light and infrared photons. In a sense, the sun's interior cools the energy down as it travels outward. Scientists cannot directly see the sun's core, or any of the inner layers, because they are opaque to light. However, we have indirect ways of probing the core. One powerful method is helioseismology, the study of the sun's vibrations. The sun rings like a bell with complex patterns of oscillations caused by sound waves trapped inside it. By observing these vibrations on the solar surface, using instruments that measure Doppler shifts as regions move up and down, scientists can infer the conditions inside the sun, much like seismic waves reveal Earth's interior. Helioseismology has confirmed the existence of the core and given us estimates of its size and density that match theoretical models. Another probe of the core is the detection of solar neutrinos. Neutrinos produced in fusion reactions stream out of the sun and have been detected on Earth. For decades, neutrino detectors observed only about 1/3 to 1/2 of the number of neutrinos predicted by solar models, a puzzle known as the solar neutrino problem. We now know the solution. Neutrinos come in 3 types, flavors, and as they travel from the sun to Earth, they oscillate or change between flavors. Early detectors were only sensitive to one flavor, electron neutrinos, missing the others. Modern detectors have observed all flavors, confirming that the total number of neutrinos matches the sun's fusion rate. This not only solved the mystery but also provided strong evidence that our understanding of nuclear fusion in the sun is correct. The radiative zone. Surrounding the core is the radiative zone, which extends from about 0.25 solar radii out to roughly 0.7 solar radii, so from 170,000 km to 490,000 km from the center. In the radiative zone, the temperature drops from about 15 million degrees Celsius at its base to around 2 million degrees Celsius at its top, and the density falls from about 20 G/cm superscript 3 at the bottom to only about 0.2 G/cm superscript 3 at the top. For comparison, water is 1 G/cm superscript 3. The radiative zone is so named because energy is transported primarily by radiation, photons moving through the plasma, being absorbed and re-emitted. This is essentially a continuation of the random walk process that began in the core. The plasma in this zone is still very dense and opaque, so photons can't travel far without interacting. However, compared to the core, the plasma here is a bit less dense, so photons have a slightly longer mean free path, distance between collisions. The dominant mode of energy transport is radiation. High-energy photons carry energy outward, getting absorbed by ions and then re-emitted in random directions, gradually creeping toward the surface over long timescales. The radiative zone is stable and layered. There is not much bulk movement of material, just photons slowly diffusing outward. This layer acts as a kind of radiative blanket, letting energy out gradually. The structure of the sun's interior, including the key zones and their boundaries, is fundamental to understanding. From its violent birth in a collapsing interstellar cloud to its current stable phase as our life-giving star, the sun is a fascinating object of study. We have traced the sun's formation from a giant molecular cloud, through the protostar stage, to the ignition of nuclear fusion and the establishment of the stable star we know today. We explored the intricate process of nuclear fusion in the core, where hydrogen is converted to helium and an immense amount of energy is released. We followed the journey of that energy outward through the sun's layers, the radiative zone where photons slowly diffuse, the convective zone where plasma churns, and finally the photosphere where sunlight escapes. We also looked at the sun's atmosphere, from the granulated photosphere to the scorching corona, and learned about phenomena like sunspots, solar flares, and the solar wind that are driven by the sun's magnetic activity. Every sunrise on Earth is a reminder of the sun's power and the incredible journey that sunlight takes. Hey, thanks for watching. If you enjoyed this video, don't forget to give it a thumbs up. Share it with your friends, leave a comment down below, I'd love to hear your thoughts, and if you haven't already, hit that subscribe button and turn on notifications.